In this video, we're going to look at the concept of continuity. Continuity is taught via the idea of being able to draw a graph continuously from left to right without lifting a pencil. So in this example, I can draw this graph from left to right without lifting the pencil or the light arrow as you see it. In this one, we have a point here, but to get to the next spot on the graph, I need to pick up the pencil and put it back down there to go across. Again, lift, put back down, lift, put back down, lift, and put back down. There's definitely a fundamental difference between this graph being able to be drawn continuously from left to right, and this graph being point from here to here to here to here to here. Again, I can't go from here to this spot without lifting it because there is no actual graph in the region you see here. This is a much different type of graph. We have the function listed here where if x is not 0, it's the function x times sin of 1 over x. I'll mention that if you have x equals 0, 1 over 0 would be bad news. So we define the function to simply be 0 when x equals 0. But we get a graph that looks like the one you see here, where you have the traditional sinusoidal type flare, but because of the value of x, we think of there being two graphs of x and negative x superimposed here. We kind of get the function trapped in. And the function does some crazy stuff because of the 1 over x near the origin. So the question is this function continuous at 0? To do this, it doesn't make a lot of sense because I don't have the ability to actually draw this graph forever wiggling in here. It'd be a good thing to look at this graph on a graphing utility like Desmos, and I'll try to post a link to that in the description below. We need the definition though, and here's the definition we're going to use. A function f is continuous at a if the limit as x approaches a of f of x equals f of a. If f is not continuous at a, then a is said to be a point of discontinuity. So let's break this down with the next slide. For the function to be continuous at a, we need three things to happen. We really only need step 3. We only need the thing that was mentioned in the previous slide. But for this to be true, I need both this to exist and this to exist. So step 1 simply says that the function is defined. That means that this thing here exists. Step 2 says the limit exists, and that says that this is true. So I need the function to exist, the limit to exist, and that the function actually equals the limit. If all three things are satisfied, we have a point of continuity. This graph shows where functions can be discontinuous. At values for x equals 1 and x equals 5, we get that f of 1 and f of 5 do not exist. And therefore, those are 2 points of discontinuity. At x equals 1, there actually is a value for f of 1 equals 3, but the limit as x approaches 1 of f of x equals 1, as we see here, where if I approach in from the right or from the left, it goes to the value at 1. Since these two things here are not equal, we have a point of discontinuity at x equals 1 as well. At x equals 3, we do have the limit, so we do have the function existing at 3, but here the limit doesn't exist, because now we have the limit as x approaches 1 from the left, sorry, x equals, I apologize, 3 from the left of f of x equals 2. That's shown with the, I'll use orange here. And the limit, push back to blue, limit as x approaches 3 positive of f of x equals 1. Going back to orange from this curve here. Since these two things are not equal, we would get that the limit as x approaches 3 of f of x does not exist. So we have discontinuity at x equals 1, at x equals 2, at x equals 3, and at x equals 5. Those are the spots where x is discontinuous. Again, discontinuity points are x equals 1, 2, 3, and 5. The next few slides simply give you rules for when things actually are continuous. If I have two functions f and g which are continuous at the point a, and any constant c, then some other functions we know immediately are continuous. I can add the functions, and that's continuous immediately. I can subtract the functions. I can multiply the two functions, or multiply one of the functions or either of the functions by a constant. I can raise the function to an integer power. I'd given it a positive integer power, like this. So for example, this might be f of x quantity cubed. But we're not going to discuss n equals n being negative on this slide. We will see that on a slide in a little bit. We can also do the quotient of the two functions like this. F over g, with g again only where the bottom function is not 0. If g of a was 0, then we would have that f over g of a equaling f of a over g of a would equal f of a over 0, which would be bad news. So I mentioned the idea of n equals -1 or being negative values. That kind of pops up in this slide. If I talk about polynomial functions, based on the information in the previous slide, those are definitely continuous. Because of the rule in the previous slide shown here, I get the nice statement on the next slide that a rational function is continuous at every point at which it's defined. So again, every point where the bottom does not equal 0. The next slide is a good example of that. This is an example of a rational function. We have the quotient of this rational function along with this rational function. Quickly remember that the roots of the numerator give you zeros, and I think I spelled that wrong. Hold on, sorry. And the roots of the bottom give you the asymptotes. So the roots of the bottom are at x equals 3 and x equals 4, and those are the values you see here. So if x squared minus 7x plus 12 equals 0, this can factor to x minus 3 times x minus 4 equals 0, x equals 3 or 4. These are the only spots of discontinuity in this function. This one's a little bit tricky to read, but it is pretty straightforward. If you have a composition of two functions and the inner function is continuous at a and the outer function is continuous at g of a, we're good to go. Because recall that f of g of a equals f of g of a. So I need that this is continuous, i.e. that a plugs well into g, but then I also need this whole thing to be a good thing to plug into f. This is a much more high-powered statement than the previous slide. I will let you pause the video here if you wish to write it down. I will mention that the option 2 is a subcase of number 1. But basically, if things behave well on the previous slide, you can do these types of limit tricks. As long as the f is a continuous function, I can basically pull the f out of the limit, taking the limit of the inside thing like you see here. This discusses the idea of right versus left continuous on endpoints of an interval. This function is very clearly continuous between the values of a and b. I can draw it back and forth even without having to pick up the pencil. However, it's not defined at b, but it is defined and defined well at a. We'll look at definitions in a second, but again, there's an idea that's very clearly there's something doing well here, but not doing well there because of the closed circle and the open circle there. Analogously, this function is left continuous at the right endpoint here. Again, it's continuous all between a and b, but now the right endpoint is well behaved on the left side, and the left endpoint is not well behaved on its right side. So here are the definitions for that. So again, the left-hand continuous, I'll mention here, this is on the right side of the interval, and this point here is usually on the left side of the interval. So if I had the interval a and b, the b is what we're talking about here, and the a that we're talking about here. So once we can define this, we can define the idea of continuity on an interval. Continuity at a point, as well as continuity on the endpoints of the screen. Previously, we can discuss continuity over certain regions, looking at some examples to make this clear. This function is continuous at every point except for 0. Again, it's not defined at 0 because the left limit would be the value of 1, while the right limit is the value of 5. However, if I look simply at the spot to the left of 0, it's completely well defined, and it's also continuous. And because of the closed circle here, we would get that it's continuous on negative infinity up to 0, including the 0. And notice the fact that we have a square bracket here. On the other side, I have the function here with an open circle there, and therefore we see here that this is an open parenthesis on the 0. So this is a little bit of a tricky definition. If you have any questions, please let me know. I can do a further example if necessary. This shows the idea of left versus right continuity on intervals. This slide is very confusing unless you simply think about what this means in examples. If I have a function taken to a rational number, n over m, then we get some certain things based on whether whether m is even or not. The reason we're worried about m being even here is that if I look at a function like x, that is obviously going to be continuous since it's a polynomial. But if I were to take that function and raise it to the power of 1 divided by 2, this becomes a much newer function. It becomes the square root function. So the blue function, the simple f of x equals x, is continuous, while this outer function is going to have some issues because, again, we need to worry about this thing here even being defined. Another example that has the same type of flavor is the one shown here. The function on the inside here, which I can call simply f of x, equals 9 minus x squared, is continuous for all values of x. However, the function you see here is continuous only when it makes sense, or only when the inside here is greater than 0, which is the region between negative 3 and 3. Now I mentioned we would technically get only negative 3 to 3 with open endpoints to start off with. We then have to check the endpoints here and here with the right and the left idea here. But again, notice that the right continuous happens at the left side and the left continuous happens on the right side. Because both of these circles are filled in, I get the closed brackets here and here. So again, this is correct. This is not quite correct. This is a function showing what its sine of x is behaved. Sine of x has no real clear reason to understand why we'd have this continuity. It simply shows a graph walking in from the left and walking in from the right. This one shows the graph of secant. Secant also looks well behaved. We have these very obvious issues of discontinuities where the function doesn't exist. Again, being this is 1 over cosine of x, this function will not exist whenever cosine of x equals 0. So if cosine of x equals 0, oops, that's a mistake. It's the same thing as saying that secant of x does not exist. And because cosine has an infinite number of zeros, there's an infinite number of places where this function doesn't exist. And therefore, it's also continuous at all points that it exists, but therefore has a lot of points, as we see here, 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 and here, the odd half multiples of pi, where the function is not continuous. This is an exponential function. This function is continuous on all real numbers. This is just as well behaved as the polynomials. This talks about continuity of inverse functions. Basically, where the one function is continuous, so is the other one. There are some issues with reversing the domain and range, but it's pretty much straightforward that where the one is before, this one is as well. This simply gives you a nice list of the different things that are continuous. All of the functions here are continuous on their domain. So again, if the function exists, you can know it's automatically continuous. The intermediate value theorem is the last concept of this thing. It is a statement that's a little bit confusing. So I'm going to go through it carefully in the next 2 slides. Suppose f is continuous on the interval a to b, closed, and L is any number strictly between f of a and f of b, then there is a number c between a and b satisfying f of c equals L. Now to make that make sense, let's look at some pictures. Here on the left example, I have f of a here, that's a f of a, and here's b f of b. So between f of a and f of b, I have this entire region. If you pick any single value on the region, for example, the value of L, what the intermediate value theorem says is there's guaranteed to be a spot on the graph right there or a c value between a and b such that f of c equals L. Now it's pretty clear it happens this way where you get the situation, oops, I apologize, give me 1 second. Let me get the pictures back to you here, I apologize. Okay, there's the point C. It's pretty clear when the graph simply goes uphill between A to B, we're going to have this nice situation. We get one value that works. The other one shows another thing that can happen. Here I have f of a on top, f of b on bottom. Again, we're looking at the region between f of a and f of b. Take any value you want, L. In this case, I actually get 3 spots. I get one right there, and right there, where f of c1 equals f of c2 equals f of c3 equals L. So the intermediate value theorem, sometimes abbreviated simply the IVT, guarantees that there is at least one c value that works. But as you see in the second example here, there could be more than one. Well, this does require the function to be continuous. Both these two graphs here are continuous between A and B, because I can draw them with not picking up the pencil. This one shows what happens if the function is not continuous. If there's a discontinuity, then there is a possibility that I pick up the pencil and go across here. So again, I have f of a here, f of b there, talking about the region between f of a and f of b. There is a value for L where there is no spot on the graph where I cross that purple line. So this would be a situation where the intermediate value theorem does not hold because the function was not continuous. The statement of the theorem is still true because, again, if you look back at the definition of the thing, it was a condition that we had to suppose it was continuous. So since f is not continuous in this example, the IVT does not hold. All right, I appreciate your time, and I hope you guys have any questions. You'll please let me know. Thank you very much.